I'm absolutely delighted to welcome Professor John Roiser back to Cambridge and back to the Department of Psychiatry in this joint CPFT Department of Psychiatry academic lecture. And Professor Roiser, of course, did his PhD in the department here and then has gone on to work at NIH, but notably at UCL, where he is a professor of neuroscience and mental health in the Institute of Cognitive Neuroscience. And we're delighted to hear you speak today. Thank you.
Brilliant. Thanks very much, Graham. And thanks very much for the invite. How I wish I could be standing in the Addenbrooke site saying what a pleasure it was to be back, and feeling extremely nostalgic, but I'll try to feel nostalgic anyway. And thanks very much, everyone, for coming. I can see there's quite a lot of people on the Zoom, several old friends and colleagues included. So great to virtually see everyone, and thanks to everyone for making the time. So I'm going to talk today about the work that we've been doing for the last 5 years or so, which has been funded by the Wellcome Trust. It's a grant that's just coming to the end. We actually have lots of new exciting data as well, in addition to this, that we're still analysing at the moment. So this is sort of the first cut of the first couple of studies. It's going to take quite a computational approach. So this talk is a little bit didactic. So I'm sort of going to go through some of the computational ideas, explain why they're interesting and important, and then it's almost like a tutorial in the middle with our work as sort of worked examples. I hope that'll be interesting for people. And basically what I've been trying to focus on in the last couple of years is to understand what are the cognitive mechanisms or the motivational mechanisms that underlie depressive symptoms, in particular those related to interest and activity. So I'll get straight on. And I'm just going to do the acknowledgements up front, because I always forget to do them at the end or it's really rushed. So these are all the people who've been heavily involved in the study, and the studies I'm going to present today, and of course lots of other collaborators, past and present, and I'm sure there's a few people on the call today who will see their own names. So these are obviously the people who really deserve all the credit. And in particular, the name on the bottom right, that's Vincent Bolton, who's a computational neuroscientist and has been a postdoc with me for the last 5 or 6 years, has done a huge amount of work on the modelling that I'm going to present. So let's start off just by putting some basics in place, which I'm sure everybody on this call is going to appreciate already, which is the idea that the interest activity symptoms in depression are incredibly important. So anhedonia, as everyone already knows, is the loss of interest or pleasure in previously enjoyable activities, and it's one of the cardinal symptoms of depression. So you have to have it in order to be able to get a diagnosis, or you've got to have low mood. It commonly clusters with other symptoms like fatigue, difficulty in decision-making, difficulty concentrating. Those tend to co-occur together. And there was this lovely study from the Institute of Psychiatry a few years ago where the data are plotted up on the right there. The GenDepth study, originally they did this analysis and then extended it to the STAR-D sample, showing that this specific interest activity cluster of symptoms predicts poor response to standard antidepressant treatment. That's clinically interesting, clinically important. And as you can see, the people who have got the lowest levels of interest activity symptoms tend to respond best to antidepressants, and the converse is true for those in the top, the fifth quintile there. That data, the hypothesis generation was done in the GenDepth sample, and then you can see extended to the STAR-D, very similar pattern of results. So we think this is an interesting thing to understand. And also, from a sort of neuroscientific point of view, we know quite a lot about how the brain's reward system works. There's extensive studies in animals, many of them pioneered in Cambridge. So there's lots of interesting work out there that we can base neural studies on, cognitive studies as well. And about 10 years ago, my former PhD student, Nir Eshel, who has now gone on to very impressive things over in the US, where he's now a psychiatrist and leading a neuroscience lab, wrote this review called Reward and Punishment Processing in Depression, Biological Psychiatry. And that was really the first time we think that anyone laid out what the sort of state of play was in the area. And at that time, there was actually very little. So there were almost no studies out there for us to talk about. It wasn't a meta-analysis or systematic. We had to take a narrative approach. And I'll show you in a few slides' time how we've managed to update this in the intervening years. So we think that reward processing is important. There's also this idea of effort. So when people talk about symptoms like anhedonia, they might say something like, well, I couldn't be bothered, or I couldn't just get the energy together to do it. It just didn't really seem worth the effort. These are very sort of common things that people say when they're depressed. And so we think this is sort of interesting from the outset. And so that's what I'm going to talk about today with respect to this effort task that we've been using in collaboration with Masood Hussain, which I'll go through a little bit later. So Masood and I, a couple of years ago, wrote this review where we sort of tried to go through the different cognitive processes that might be important in symptoms related to amotivation. And Masood is very interested in apathy from a neurological perspective. I'm very interested in anhedonia from sort of psychiatry and mental health perspective. But obviously these two constructs overlap quite a lot. Probably their neural mechanisms and their cognitive mechanisms also overlap quite a lot. So we've gone through, there's lots of different stages that we think are potentially important, lots of different cognitive processes. And some of these are quite easy to measure in humans, some of these are quite hard. So things that are hard are things like directly measuring motivational arousal. That's kind of difficult. So you could do it by self-report, maybe some kind of physiological measure. The actual, consummatory impact, the hedonic impact of interaction with the reward, actually enjoying the sucrose solution, or how much you enjoy receiving that money, that's kind of hard to measure behaviorally. Again, that's probably going to be self-report. But there are other things that we can measure a bit more easily. We can measure things like people's decision-making, which choices they make, and how easy they find it to weigh up different decisions according to their associations with reward or effort or time and risk, and then transferring that through to a selection of an option. We can also measure things like how much effort people put in, how speeded responses they make are, or how much effort they put in. And we can measure things like learning from outcomes. So these are sort of classic reinforcement learning studies that rely on things like prediction error. So this is a kind of general framework in which we're operating. And the stuff that I'm going to show you today all sort of falls firmly within this cost-benefit decision analysis stage and option selection. But of course, the other ones are very important. We actually recently completed a meta-analysis, and so I'm very happy to actually be able to present it today in the talk, because it was only accepted yesterday in Journal of Psychiatry, and so we did a systematic review and meta-analysis of all of the studies that we could find, actually including one of yours, Graham, as I recall, where we got the data from you, where people had done case control studies of depression, and we found robust evidence for impairments in decision-making, in a test of reward bias that was been popularized by Diego Pizzagalli, and in reinforcement learning, so the ability to use past outcomes to inform future behavior. And you can see there's some variability in the effect sizes there, so this reward bias measure seems to be quite sensitive. Interestingly, that reward-related speeding measure, that's measured by tests like the Molecular Intensity A task. When she was in Cambridge, created a...
Sorry, I'm just going to, I don't know, Dominic, if you can mute everybody or if people could just make sure to mute themselves, because there's just some background noise.
Thanks, Graham. I'll carry on. So this reward-related speeding measure, which is basically do you go more quickly for high probability versus low probability rewards, or high rewards versus low rewards, actually didn't turn out to be different between depressed patients and controls in all the studies that we looked at. So there isn't some evidence out there, but actually not that many people have looked at effort specifically. So actually these three studies down here, some work by Michael Treadway in particular has looked previously, and they do seem to give us some indication that people with depression are sort of less driven by rewards, possibly more put off by the effort, if you like. So that's what we were going to try and set out to do. So how do you measure that kind of motivation in the lab, the willingness to engage in effortful activity? Well, it depends on lots of things. It depends on how you're feeling on that day, how much reward you might get, how much effort you might have to put in. So let's say I was going to ask you, are you prepared to do 20 press-ups to get $10? And a nice young fit chap like Graham would probably say, yeah, I'll probably go for that. But then let's say I changed it and I said, well, what about if I tell you to do 1,000 push-ups and you're going to get $10 for that? And you probably say, no, I don't think it's really worth it. So those are the kinds of cost-benefit trade-off that we're looking at in these kinds of studies. So we do something very similar in the lab in our task. This is the apple gathering task created by originally Masood Hussain, my former ICN colleague now in Oxford. And this is an effort-based decision-making task. And we basically parametrically vary the amount of reward you can get. So we've got the different reward levels here. 3, 6, 9, or 12 points, and then got 4 different effort levels. And effort here is actually physical effort. So we're getting people to squeeze this gripper here. And what we do at the beginning of the experiment is we calibrate it to their own grip force. So we say squeeze as hard as you possibly can. And then we get them to do different levels of effort calibrated to that. So 20% or 40, 60 or 80% of their own maximum. So it's nicely calibrated on an individual basis. And one of the good things about this task is that people can always do it because we're calibrating it to their own ability. So what that means is this 80% is definitely going to be achievable, or as achievable as the 60, 40, and 20%. So we're really measuring the effort processing and not, say, some kind of probabilistic discounting where people think, oh, I'm not actually able to do it. So we really want to try and get at the effort itself here, and that's an important feature of the task. And so we run a reasonably large pilot study with about 100 people in it. This is my former research assistant, Alan Gray. And what we basically measure is the probability of accepting an offer. So do people want to exert the effort in order to get the reward? Or they can just skip the trial. If they don't think it's worth it, they can just say no. And you might think, well, why would anyone say no? They may as well have a go. But that's not ever the pattern that we see. Across individual participants, this is extremely reliable. So there are certain levels of effort which people are very reluctant to take if they're only going to get a relatively small amount of reward. And I should say here that we are paying them according to the points they receive. So by not taking the trial, by not accepting the trial, they are foregoing their ability to actually win real money here. So we see, as expected, the significant effect of effort, significant effect of reward, and the significant effort by reward interaction. So back when I was a junior lecturer or PhD student or postdoc, this would have been the end of the analysis. But instead, now we have computational modeling, which I've become very interested in over the last 10 years. So now what we do is we're going to build a computational model and try and submit these data to some kind of mathematical analysis where we can try to tease apart the different processes that we think might be driving this pattern of behavior. And that's really the aim of the computational approach. So this is what I call theory-driven computational psychiatry. So what we do is we start with a model. We start with basically a mathematical expression of a model, how we think people are doing the task. So what sort of cognitive processes we think are going on, and then we write those down in algorithmic or mathematical form. And then we have variables in there. So we got things that can change over the course of the experiment, like the reward level or the effort level here. And then we also have constants in those equations, and those constants are called parameters here. So the parameters change things like how sensitive people might be to the reward and how sensible they might be to the effort. And then on an individual basis, we can estimate how important those parameters are for each individual. So for one person, effort might be really important and reward might not be very important. For another person, it might be vice versa. So this estimation procedure allows us to get a handle of that and produce summary statistics for each individual, just like using a standard behavioral analysis, we would calculate, say, the difference between conditions. It's just a different way of going about it. And then we can build different models. So we can build some models that have got different parameterizations of reward and effort, for example, and look to see how they trade their explanatory power, because more complicated models tend to always do better, just like more complicated standard regression would tend to fit the data better, and how that trades off against the complexity. So we penalize the models that are more complex, and we benefit the models that do better in terms of the percentage variance explained. And through that, we try to identify a parsimonious model. And then at the end, a very important step, we need to check how well this model really recapitulates the patterns in the data. And often that involves a creation of surrogate data. So data where we know what the ground truth is. We run the task on our model, so we get the model to make the decisions, and then we try to get these parameters back again and see how accurate we are. And when we go through this whole cycle, often we realize at this model checking stage sometimes that the model's a bit misspecified. Maybe there's some important parameter missing. Often that can mean we create a new model, and then of course we go all the way around again. So that's basically the approach that we're taking in this kind of cognitive computational modeling. Okay, good. I hope that's all clear. I'm going a little bit quickly because I think there's some people who are already a bit familiar with this, but we can always come back to it. I'm going to go through the worked example now. So what do? Well, we start by specifying the model. So we have to write down some equations that represent the cognitive processes that we think are going on when people do this effort task. And this is the model. Don't be too scared. It's just a bunch of equations, and we'll go through them one by one now. So we've got different terms here, and this is a sort of graphical depiction of the model. So we've got the subjective value of the offer, and that involves the reward sensitivity and the effort sensitivity. And then that's obviously going to be influenced by the precise offer that's out there. So maybe a lot of points for a small amount of effort. We then have a bias parameter, which allows us to get an idea of whether people are generally more likely or less likely to accept reward. And then we have some decision noise on the top because people aren't perfect. Sometimes they just make the wrong decision. My colleague Peter Dine used to like to call this the shaky hand parameter. So you just accidentally press the wrong button, or I sometimes think of it as the shaky brain. Sometimes you just not paying attention. And then through that, we can generate the choices that we think people are actually making. So let's start with the reward. That's here. So that the constant term, the parameter is called theta r. And so that basically determines the slope of the reward function here. So you can see some people aren't very sensitive to reward. As you increase the reward, it doesn't make much difference to the subjective value of the offer, and other people are very sensitive. So I hope that's easy enough. Then the second term is this effort term. This has got two parts. It's got a linear term, just like the reward, but also a quadratic term, which gives it a curvature. So the effort parameters tend to be negative, as you can imagine, because people don't like exerting the effort. So you get a linear term like this. But then we also have this quadratic term, which allows these lines to either tail off a bit or sort of start going down catastrophically. And so that's the positive effort and negative effort quadratic terms. And then put them together and it generates this effort cost profile. So sorry, I should have just pointed over here just before. So this for some people it sort of tails off, and for some people increasing effort seems almost catastrophic. And for some people it's zero and they just show a linear effort term. So that's the effort sensitivity and reward sensitivity parameters. We add those together and we get an overall value of the subjective offer. So it's just the subjective value of the offer. And now we have that value, so we need to create probabilities of which people are going to say, yes, I'm going to go for it, or no, I don't think it's really worth it, I'll move on to the next trial. So we run these through a sigmoid function, which is just a logistic curve. And you can see here that for some people, they've got a very high bias, so they'll tend to accept things more, and other people got a lower bias, so they tend to accept things left. It just shifts the curve left or right. And that's independent, importantly, that's independent of the subjective reward value and the subjective effort. And then finally, we've got this term here, the noise parameter. It's called an epsilon greedy process. And basically, this theta noise just says, well, every so often, on a certain proportion of the trials, I'm just going to, just choose at random. I'm just going to ignore all of this processing, all these calculations we've done up here. I'm just going to choose totally at random. And so that theta noise parameter gives an indication of how random people are in their responses in a way that's totally independent of the effort or the reward. Okay, good. Normally I'd be able to see the audience, so I get an idea of whether people are sort of staring at me in blissful incomprehension or everyone's really, really tuned in. So I'm very much hoping it's the latter here, but do feel free to ask me if anything is unclear. Okay, great. Oh, thanks very much. Some thumbs up, I like it. So the next stage in the theory-driven approach is the model estimation. So those thetas, theta r, theta e, we have to get hold of those for each individual participant. And that basically what we do is we jiggle the model around, we jiggle those parameters around until we get the best fit for the data. That's the simplest way of thinking about it. You can do this using maximum likelihood. It's a bit rubbish, it doesn't work that well, and it allows the parameters to drift off into slightly random parts of parameter space. We use hierarchical parameter estimation using Monte Carlo Markov chain simulation, and we do this in this software package called Stan, and it works really, really nicely. So we gradually evolved, like the rest of the field, over about a decade from relatively simple estimation functions like maximum likelihood through maximum a posteriori, then we did expectation maximization, and now we're here at Stan. Who knows where we'll be in the next couple of years' time, but it just shows this is a very rapidly developing field. But we're pretty happy with this approach. And so what this allows us to do is basically to estimate all the data at the same time. So it's like a multi-level regression model. So we have these population level parameters, which are sort of means and standard deviations of the parameters themselves at each individual level. And then we have the individual level parameters. And we estimate, as I say, all of these at the same time. And the prior here, so this population level parameters like a prior, it comes from the data themselves. So we're not imposing anything. It starts off very, very flat. And as you can see, we've got different priors for the different parameters here. And then the next thing we want to do is the model comparison. So we've got lots of models. Vincent, my postdoc, built lots of models, and then we want to see which one does best. And as you can see, he really did do a lot of models. There are, I think, 70 models on this slide. Various different parameterizations of effort. We put a curve in there, took the curve out, the curve and reward, took the curve out, different types of curves, quadratic, exponential. We tried a huge number of different things, tried putting some of the parameters in, taking them out. And as you can see, there are different families of models that tend to do well. They're clustered together here in the plot. And the one that did best is the one that I showed you. So that's with linear reward, linear effort, quadratic effort parameter. This K is the bias term, and the L is the noise parameter. But you can see there are other ones that are quite close. So, for example, one without the quadratic term does a little bit worse, but not a huge amount worse. So this sort of basic structure is fairly constant. But this is the one that we end up estimating the parameters from because it's the one with the best model evidence, and it convincingly wins. Even though these numbers don't look very big, this is a log scale, and this is 1,000. So there is a substantial difference even between these two models that are quite similar. And then finally, what we need to do is check the model. So how well does it actually recapitulate the patterns that we see in the data? And can we recover these parameters so doing this estimation from a surrogate data? And the answer is it does a pretty good job. So this is the original data that I showed you just before. And then this is the model data. So this is what the model predicts. And as you can see, they look pretty similar to each other, which is a relief. And then we can look at that in surrogate data. So here's where we've taken a bunch of parameters, and then we have simulated data because we've got this model now. So we can say, well, for each trial, what choice do you think the model's going to make? And then we can try and recover the parameters from those choices, and then we can compare those to the ground truth, which we know because we set it in the first place. And so we get a pretty good recovery of the different parameters here. And then we can also do things like predict on an individual participant level, so these are each of the individual participants, how much they're going to, say, accept the offer. So it's more crude model agnostic measure that we would typically get out of these kinds of tasks if we weren't doing a computational analysis. As you can see, again, it does a pretty good job. Okay, so now the interesting bit, because we actually get to look to see what the parameters look like and how they associate with different symptoms and diagnoses. So we had a whole ton of questionnaires, and we thought some of them probably measure the same kind of thing. So we did a factor analysis, and we end up, so these are all the different questionnaires, which I won't go through for the sake of time. But we basically get these 4 factors out. One of them really relates to depressive and anxious symptoms. Remember, this is a non-clinical sample, or I should say an unselected sample. Some of these people do have relatively high rates of depression and anxiety, but they probably wouldn't meet diagnostic criteria. And then we've got a factor that probably relates to apathy. So the apathy evaluation scale loads heavily on this, as well as a few things from the UPPS. Factor 3 is one that I think is interesting because the anhedonia scales cluster on here. So this is the Chapman Physical Anhedonia Scale. We've got the TEPS here, which some people might be familiar with. Also the SHAPS, which is a commonly used scale. So they tend to go together. And then I also put in these scales, which are quite commonly used in clinical psychology research, relating to dysfunctional attitudes. And they didn't seem to load onto any of the rest of these. They load onto their own factor. And we actually never really see correlations with these dysfunctional attitudes, which is interesting. So then what do we see in terms of the correlations with parameters? So the first thing that we see, which has actually been replicated many, many times before, is an association in this unselected sample of the sensitivity to reward. So if you remember, this is the linear effect, so it's like the slope of the reward sensitivity function. And that correlates with people's levels of depression and anxiety. There's a bit of pessimism sitting in here in this factor. So these are the factor scores. sitting on the y-axis here. As you can see, as people become more and more reward insensitive, they tend to have a lower mood and a higher anxiety. And as I say, this has been seen in lots of studies in healthy samples in the past. From my perspective, a more interesting and novel result was this association with anhedonia. So here we saw this quadratic effort sensitivity parameter. I think we also saw a similar effect with the linear sensitivity parameter. So this is the extent to which the effort subjectively sort of tails off as the effort level goes up, or whether it sort of increases catastrophically or disproportionately, correlates with anhedonia. So the people who show this sort of more catastrophic effort profile so they're more effort sensitive, they tend to be higher in anhedonia, and the people who show this more tailing off type profile tend to be lower in anhedonia. Okay, great. So we were encouraged by these results, so we decided to embark on an enormous study, which took many years. Now my PhD students, previously research assistants, Anna McKershall and Madeline Payne, did a huge amount of this work. So we've got a big sample, nearly 200 people in the sample in total, and it's split into 4. So this was one of the core studies in the grant the Wellcome funded. And so we've got what we're calling controls. So these are people who are very carefully selected. They have no personal history of any mental health problems, and they have also no family history of mood disorders. Then we've got a group that we call relatives. So they have no personal history of mental health problems, but they have a definite family history. So a first-degree relative, so that's a parent or a sibling or a child who has been diagnosed for depression and treated for depression. Quite hard to recruit, actually, so we didn't get quite as many as we'd hoped for here. We were hoping for 15. And then we've got a remitted depressed group. So these are people who have been depressed in the past and are now better. And then a currently depressed group here. And as you can see in the symptoms, the remitted, the relative, and the control group, they all have pretty low levels of symptoms, still a little bit higher in the remitted group, as you might expect, but not nearly as high, of course, as in the currently depressed group. And these anxiety and anhedonia scales show a sort of similar expected pattern, which is reassuring. Okay, so we ran this task along with several other tasks that I'm not going to talk about today in all of these people. And we had to exclude a few people. One for problems with calibration. So I'm being a bit generous here. So this is when people seem to be much better at squeezing in the main game than in the calibration test that we did at the beginning. So they squeezed at least twice as hard in the main game as the calibration test. And this is something that we to use a technical term called cheating. So we excluded them because we don't think they're trying very hard in the calibration. There are a few people who we excluded because we weren't confident in the diagnoses. And they're not included in the previous graph, I should say. And then there was one person who didn't really seem to be behaving very consistently on a lot of different tests. So they were a multivariate outlier, so we excluded them. But these are the only exclusions, and then everybody else gets included. And as you can see, we've got a very similar pattern to the previous study. So effects of effort and reward and the interaction. And interestingly, this effect of group. So that suggests that some of the groups tend to be less inclined to exert the effort than other groups. So the computational modeling allows us to ask why. So that's what I'm going to go on to now. So if you look at these graphs, it might be a little bit difficult to tell. So this is the same graph as before, just split by the different groups. And you can probably see the controls and the relatives at the highest effort level with low reward. They do it some of the time, so they're inclined to say yes some of the time, but it's a little bit lower in the remitted and the depressed group. And similarly, you might be able to see that some of the other bars are a little bit higher here than they are. But it's quite difficult to tell just by looking at it by eye. We could go through and do pairwise comparisons here, but actually the computational model is a much more principled approach to answering this question of why is there this difference between the groups. So we build all these models again. I say that as if it takes no time. This is months of work, obviously, for poor old Vincent. And then we do the model comparison again. And brilliantly, the same model wins, which I just think is a stunning result because it really suggests that our model comparison has done a pretty good job. But it's this very same model. It's got the lowest information criterion, and it's the same one as we used previously. And then we can estimate the parameters. So we've got this bias term, that's the one that moves the sigmoid to the left or right, the linear reward term, the linear effort term, and the quadratic effort term. And it's a little bit difficult to see here, but basically the thing that really discriminates between the groups is actually this bias term. So if we just plot it using more traditional error bars, we can see that the two clinical groups, the ones who've definitely had depression, are lower in the bias term than the two non-clinical groups. So the people with depression are showing a reduced tendency to accept the offer, and that seems to be independent of the reward level. There's maybe a slight reduction in reward sensitivity, but it's not significant. The effort sensitivity looks very, very similar, as does the quadratic effort sensitivity. So what we've identified here is sort of a general tendency just to say no, so they don't want to do the task, and it doesn't really matter how big the reward is, and it doesn't really matter how much the effort is. And this is an insight that we couldn't have got if we hadn't gone through this computational process. And we did look for symptom correlations again. This is a little bit more tricky when you've got this design, because of course the depressed patients have got much, much higher symptoms than everyone else. So we tried doing some correlations in the depressed group alone. We did see this correlation between apathy and effort sensitivity, but there's a lot of multiple comparisons here, and I don't know if I believe it, especially because it does appear to be going in the wrong direction. So we weren't blown away by the symptom correlations here, and we did see some correlations in the other three groups where the symptoms were all more similar, but again, none of them really showed very strong levels of significance. Okay, so now I'm going to come on to the last study. Hopefully, they will still have lots of time for questions. And this is one where we've basically tried to see whether we can manipulate these parameters that we saw in the previous study. So we're using the same task again. And this study is being conducted by Shamathala Hakoon, who's now clinical PhD student in Oxford, and Carol Kieslis, who's going to start a PhD shortly at UCL. And in this study, what we've done is we recruited depressed and never depressed people, similar criteria to before, and we've given them a dose of L-DOPA on one occasion, and we've given them placebo on another occasion in a crossover design. So this is all a within subjects comparison. And then what we want to do is to see whether L-DOPA affects any of these parameters from the computational model. So I'm going to cut to the chase because we don't have a lot of time. But you can basically see that, rather disappointingly, even from these graphs, it doesn't look like the L-DOPA has done an enormous amount. So this is the controls under placebo and the controls under L-DOPA, and you can see the overall pattern is extremely similar. And the same is true in the depressed group here, interestingly. And if we go through and look at the model comparison, we can see that we get the same model again. So this is, again, great news because it suggests that this is generalizable across our different studies. But when we look at the parameter estimates, possibly unsurprisingly, because of the patterns that we are seeing here, we actually don't see any marked discrimination between the different conditions. So there's maybe a hint of a reduction in the bias parameter. That's similar to what we saw in the previous study. This is a totally independent sample, I should say. Nothing in terms of reward sensitivity, which is what we might have predicted based on the correlations that we saw in our pilot. The effort sensitivity, it's not very convincing, it's certainly not significant. But there is this, maybe this hint that the effort is becoming sort of less subjectively effortful, both in the linear term and in the quadratic term here, only in the depressed group. But there's a complication, because when we were looking at this, we thought about different variables that might be impacting this. And one of the things that we were really worried about is the dose. Because what we did is to give the same dose of L-DOPA, I think it was 150 milligrams, to everybody. And it didn't matter what their weight was. So we haven't titrated the dose on an individual basis. We thought it would be technically too difficult for us to do on the day. But what we did do is we took plasma samples. And so we looked at the dose, and indeed we saw a relationship, which I'm not going to show here, between how heavy someone was and the effective dose, so basically the plasma concentration of L-DOPA. This made us think, well, maybe we should start including these things as covariates in our model. And when we did that with weight, we found something rather unexpected. So what I'm showing here is the correlation between the effect on this linear effort parameter, which hasn't shown a significant effect overall, either in the group comparison or in the L-DOPA comparison, and the weight. So what this means is that if you go up here, you become less sensitive to effort, because this is a negative number to start off with. If you go down here, you're becoming more sensitive to effort. And it's a really robust looking result. Love to hear what people's opinions are on it. I've got my own ideas. And initially I thought this was brilliant. I thought, wow, we've got such a lovely result here, because we've got this dose dependency, because the heavier someone is, the less dose they're getting, so the less effective the L-DOPA is going to be. And then I realized that's the opposite of what is shown on the graph here. But actually, it's the people who are heavy. So, most of the people here above, 85, 90 kilograms are probably reasonably overweight. And if you look, these numbers here are all above 0. So these are the people who are getting the lowest effective dose, but they're the ones who are experiencing the greatest reduction in the effort sensitivity parameters. So these guys are becoming less sensitive to effort. Whereas, it's a bit noisy down here, but maybe these ones are becoming a little bit more sensitive to effort. And one obvious question is it just gender, because the groups are matched for gender? And it isn't. So you see this relationship both in men and in women. And then another obvious question is, well, is it just due to some kind of regression to the mean? Is there some difference on the placebo? And again, there isn't. So this is the relationship on the placebo condition. And this is the relationship on the L-DOPA day. And as you can see, everything in this graph here is really driven by the L-DOPA. So it's a really robust looking result, but we're still struggling to understand exactly what it means. One idea that I've had, I can't remember if I saw Paul Fletcher's name on the call, but one idea that we've had is maybe this might be something related to obesity, and possibly the effect of obesity, maybe an inflammation on the brain's dopamine system. So maybe overweight people could be more sensitive to the L-DOPA because they've got something something different about their dopamine system to start off with. But that's extremely speculative. And, who knows really? But it's a really interesting potential for the future. Okay, great. So I'm just going to stop here. I'll just conclude by saying what we've learned is that depression is associated with a general lower willingness to engage in effort. It's very unclear whether this is a risk factor or a consequence of depression. We saw it in the remitted group, but not in the genetically at-risk group. Symptoms reveal a slightly more nuanced picture. We found this association between mood disturbance and low reward sensitivity, and anhedonia and effort sensitivity, but we couldn't see that in the clinical group. And we didn't see any effect of L-DOPA on reward sensitivity, which is what we'd hoped to find. But it did seem to be affecting specifically effort sensitivity and none of the other parameters, but in this weight-dependent fashion that we're still trying to figure out. And with that, I will stop, and I think we've probably got about 20 minutes left for questions.
Fantastic. Thank you very much indeed, John. And we do indeed have some questions. So I'll just ask, I see that Laith has got a question. So Laith, if you would like to have a crack at unmuting yourself and asking your question, please go ahead.
Hi, yeah. Thank you for the talk, Jonathan. I think you've answered my question in this conclusion slide, really. But just to clarify, so in the task that you described, is it essentially that the depressed and the depressed group, the remitter group, have just a higher activation energy to start on the task? Is that the right sort of understanding? And then once they get started, they perform very similarly. Is that right?
I don't know if I think about it in activation energy. I guess I would think about it in terms of whether there's any relationship with the reward or with the effort. So I guess one way you could think about it, if you were running a drift diffusion model or something, is they have a slightly lower bias towards the yes side. So just in general, across all the different reward and effort levels, they're just more likely to say no. And there's an interesting question as to why that might be. It could be because they're less confident, even though everything's calibrated to them. It could just represent a general conservatism. We see this in other settings that directly related to effort. So on decision-making tasks, we see a slightly more conservative profile. People have measured this on the Cambridge Gamble task as well. But for me, to my mind, the interesting thing was the lack of association on these other parameters, which is what we had anticipated.
Thank you.
Thanks,
I see that there's a question from Katerina Zulsdorf. If you've got, are you able to ask your question, please?
Yes, I am. Thank you so much for your talk. I was wondering what you used for the model comparisons. Was it, I saw it was the information criterion. Was it the BIC or the AIC?
Yeah, so when you use STAN, you can't really get the AIC and BIC easily out of STAN because it's taking a totally different approach. It's basically sampling the parameters directly from the posterior. What you can do is a sort of cross-validation. So you can sort of leave out half of the data, or you can do sort of leave one out. It takes a huge amount of time and computational power, but you do get pretty robust results. So we've used, I think, something called the WAIC. I'm trying to remember what the W stands for. But it's, it is similar to these other information criteria. It just doesn't make any assumptions, because in AIC and BIC you have to assume what the impact of the number of parameters should be. Whereas here you don't have to make any assumption like that. Everything is taken care of through the cross-validation. So we think it's a pretty robust technique.
Okay, so you don't take into account the number of parameters per model? Does it penalize for that?
You do effectively, because if you've over-parameterized the model, then when you do the cross-validation, you won't get generalizability, if that makes sense.
Yeah.
So it does take it into account. It just doesn't make any assumptions, because in AIC and BIC, there's a specific equation to say how much you should do the penalizing by, but those are only estimates. So it's a way of doing that without having to make those assumptions.
Okay, thanks. And did you implement the MCMC in R?
Well, it's all done in STAN. Ultimately, you can access STAN through Python or R or MATLAB. I think Vincent did it through MATLAB because he likes MATLAB. But other people in my group do it through R. You would just get the same answers.
Okay, thank you.
You're welcome.
John, could I ask what the strategy is to take this work forward into clinical practice?
What a great question. So I think when you're doing case control studies, it's always very difficult to see, what the potential clinical utility is. The way that I see it is that you really have to embed these kinds of tasks in either a sort of risk study, so some kind of longitudinal population cohort, which could probably get better at questions around causality, which is one of the things that we wanted to measure here, but we didn't. But that's one strategy, and I've been trying to do that with some colleagues in UCL in our psychiatry and population health departments, because we've got lots of good birth cohorts at UCL. But I think actually the key way to do this is to embed these kinds of mechanistic and computational measures into randomized controlled trials. So in studies where, a little bit like the L-DOPA study, where we just looked at a one-off dose. There's lots of advantages to that. I think I saw Camilla earlier was on the call. But Camilla tried doing this when she was doing her PhD in my lab. And it really allows you to ask these subtly different questions, which is whether the medication has an impact, but also perhaps more importantly, does it have an impact disproportionately in some people more than others? And that's the thing that I'm really interested in, because I don't believe that depression is a sort of unitary mechanistic entity. I think it's more likely to be a sort of umbrella term that's covering lots of different mechanistic dysfunction at the level of the brain. And so, to my mind, in a sort of inherent part of this dimensional approach, of which computational psychiatry is a part, the power is going to be in doing things like stratification and prediction of treatment response, which, as the psychiatrists on the call know, is quite difficult to do at the moment in practice, and there's a lot of trial and error in deciding things like which medication to give someone, or whether they should have a psychological or a pharmacological intervention. So that's the approach that I think is most likely to bear fruit. The downside is these are very expensive and time-consuming studies to do. You need to power them appropriately, because if you're looking for associations, for example, that exist in your intervention group and not in the placebo group. That requires a lot of statistical power, a lot of samples. But I think it's probably worth it. So, for my next grant application, that's the sort of approach that I'm going to be trying to take. But it does take a long time to get there. So no easy answers.
Thank you. I can see the question. Apologies, I'm not sure how to pronounce your name, but Svelandi.
Thank you. It's Shri here. Thank you. Thank you for an excellent talk. I was just wondering, it made me think about reward sensitivity and perfectionism to a certain extent, and its relationship with mood. And I was wondering whether you had any thoughts or in terms of how we associate reward sensitivity with an inherent kind of temperament trait in terms of perfectionistic aspects, and how does that link in with either effort or motivation and as a consequence mood?
Sorry, did you? I didn't mean to cut you off there. Did you just want to finish?
That's it. Thank you.
Okay. Thank you. Sorry, it's so difficult on Zoom because you can't see anyone. So the closest that we've got to that answer is this dysfunctional attitude scale. So there are questions in here that relate to perfectionism and also pessimism and attribution of negative things happening. They all seem to cluster together in our analysis. So when we do the factor analysis, there's two scales here. One of these I think is maybe even called perfectionism. I'm sure the clinical psychologists on the call will correct me. I'm wrong about that. And they always factor into the same factor. And we have never seen any evidence that these are associated with any of the parameters. And they also seem to be dissociated from the other factors here, so apathy and anhedonia and the low mood per se. And that sounds like a sort of unexciting null result. But I actually see it as quite interesting because to my mind, it does sort of reinforce this idea that we really do have these separate dimensions of function in depression. And some of the things that we're talking about are going to be very relevant to these, what I call very low-level or bottom-up processes like effort or reward sensitivity. Whereas something like perfectionism, I think of as being much more related to negative schemata and there in the name, isn't it, the dysfunctional attitudes, which are sort of developed over time and maybe need a different sort of intervention that it's very difficult to actually treat from a pharmacological perspective. So I guess in summary, I would say I don't think we have any evidence that those are associated, but nonetheless, I don't discount it as a very important dimension of depression. It's clearly the basis of very, very successful psychological treatments.
Thank you. Thank you.
Angela, you have a question, please.
Okay. Jonathan, hi, it's Angela. I thought you'd like to
Hi, Angela. I was thinking of you when I was writing this talk because I remember the last talk I came to.
There really are people out there listening to you. This is a naive question because I'm not that strong on modelling. But in some ways, I was wondering, are you not surprised that the same model is applicable to depressed and controlled subjects? And related to that, is there not individual differences in the kinds of models that describe even individual control data?
Yeah, absolutely. Not in the slightest bit a naive question. I have to say, I don't think I was surprised that the same model fitted the different groups because in depression especially, it isn't, I don't think, mechanistically unitary. So I don't think it's a single entity, and there's going to be a lot of overlap with the general population, like non-depressed people. And also in the first study, it's quite possible that we had a few people who were a bit depressed, or maybe might have been depressed in the past because we used an unselected sample. But I guess more generally, I do think of these things as being much more dimensional and categorical. So it's a matter of degree as to how sensitive to effort you are. Not are you sensitive to effort at all? That would be removing the parameter from the model altogether. So I'd have been very surprised, I guess, if we hadn't had, say, a reward sensitivity parameter or an effort sensitivity parameter in the model. The precise form of that parameter, the fact that it comes out as being a quadratic term every time, I guess, is a little bit surprising. You are absolutely right about the different the different individual variability. So when we do these analyses, it's done on aggregate in a multi-level modeling framework. So when we get the evidence, it's the evidence on an aggregate across everybody. And one thing that we have seen is, sorry, I'm just going to go back to this slide. So this equation here, this parameter with the noise parameter, that is different in different people very clearly. So all of these just vary continuously. And I don't think there is a few people who have a 0 on the quadratic effort sensitivity parameter. But most people are either a bit positive or a bit negative. The noise parameter actually only really applies to probably 5 to 10% of the sample who have, say, a noise parameter above 0.01. That would mean 1% of the time they were making these random decisions. Pretty much everyone else sits at 0. But in this modeling framework, if the parameter is sort of redundant, or it's not necessary, it'll just get assigned a value of 0. So that will still be taken account in the model comparison. Sometimes we do get results where this parameter drops out if we've got a specific sample where there aren't many participants who need that noise parameter. So it definitely isn't totally consistent across participants. But I think the modeling can sort of take it into account because the parameters just go to 0 in those people who don't need them. And if there's enough of them, then the parameter will just drop out altogether.
I guess the thing what made me think about this particularly was when you were explaining it, which I thought you did beautifully, all about the development of this model, and you were showing the different directions that reward effort sensitivity and reward sensitivity could go in terms of whether it's kind of just tends to just generally decline for effort or generally go up for reward, or alternatively some catastrophic effects in one direction or another. And I thought, unless I misunderstood, that ultimately you had a model that on the whole tended to be relatively linear for the sensitivity for reward going up and one which was relatively linear for effort going down. And I was thinking, but surely there are some people who might show a catastrophic effect for effort, or
and that's why
effect for sensitivity reward.
I would say, yeah, so if we just go back to the data. So on average, you can see that's basically true. So, it's largely linear in the effort profile. But the reason this quadratic parameter gets selected is because indeed there are some people who have positive effort profiles and are some people who have negative effort profiles. And I skipped over these because they're a little bit difficult to see for the group comparisons. But as you can see for the effort sensitivity parameter, some of the people are positive and some of the people are negative. So what that allows for is the very fact that there are these individual differences, and some of them go up and some of them go down, tailing off versus catastrophic.
Okay,
yeah.
I see.
So, yeah,
okay,
not naive at all, but yeah, very important.
Thanks, Jonathan.
It is a real challenge in modelling, how to deal with these individual differences. I think anyone would concede that.
Thank you. So we have time for one or two more questions. Pranathia's got a question that she can't ask because she hasn't got a mic, so I'm going to ask it for her. And she asks whether pessimism could be a potential confounding factor, such as there's no point trying because I never win anything anyway. Could that be important?
Yeah, it could be. I can't remember if we've specifically looked at associations with pessimism, but our pessimism questionnaire, which is called the LOTR, what is the optimism questionnaire, that loads on these sort of general depressive and anxious symptoms. So if we were going to see an effect, I think we would expect to see it with this factor 1. Interestingly, if you remember from the first study, that actually the main association we saw was with reward sensitivity, not with the kind of general predilection to exert effort. So yeah, it's certainly possible. Another way that I've thought about this is in terms of confidence. So in a future study, I thought it'd be really interesting to get people's confidence on a trial-by-trial basis, because that might explain, and that's a bit similar to pessimism, and that might explain whether people are not engaging just because they don't think they will be able to do it. But in general, people can do it. I want to make that very clear, so I'm just going to run to the very end. Basically, you can see that people can generally do it. So these are the success rates, and this is the success rate in the case control study. Every so often they do fail, but it doesn't vary very much. The failure doesn't vary that much across the different effort levels and reward levels, maybe a little bit at the very highest effort level, but probably not perceptible to the participants given the number of trials they do. And this success rate doesn't correlate, I think, with this tendency to not go for it. So I think it's still a bit of a mystery. But at the moment, I'm interested in thinking about it in terms of competence.
Thank you very much, everybody. I think that covered also one of the other questions that was in the chat, Mazaffar's question. We'd better draw it to a close. I just thought, thank you very much, John. And I think one of the things I was going to say at the beginning, but I'll say now, is Professor Roiser has a great interest in education and graduate education. I think that certainly came through in the way that you really helpfully, thank you, explained this computational modelling and demystified it, because it can seem very obscure, certainly the first time that people come across it. So thank you very much for that and for sharing your insights into these processes.
The reason is, Gwen, that I remember what it was like when I didn't understand computational modelling. So I always try to think I would have explained it to myself, because it can be extremely obtuse.
Yes. Yeah, well, thank you very much for that. And so please, everybody, join with me either virtually or if you have your microphones in thanking John very much for speaking to us. Thank you very much.
Thank you very much, everyone. It was a real pleasure. Thanks for all the great questions as well.